tautomer. And so you can take your ketone, and I'll just draw, and I'm specifically putting in an extra methylene here so you can see what happens. So we have here the keto form of this ketone. But it's not the only form that this thing can take on. There is this rapid dynamic equilibrium that can exist, and it actually favors the keto form for simple ketones, but we can have what's called the enol form. And this is our enol. En, right, because there is the alkene there. Ol, because of the hydroxyl group. So these are structural isomers. That's important to note. Let me write that down. These are structural isomers. They are not resonance forms. And they're in rapid equilibrium. The keto form is generally favored, but what allows this keto-enol tautomerization, or in other words, enolization, to occur? We have a bunch of different words for this, right? So enolization, right, you form the enol. Keto-enol tautomerization. Tautomers are each of these forms. So they are structural isomers, not resonance forms. So they basically differ in the location of a double bond and a hydrogen. So that's the first thing you notice. These things only differ in the location of a hydrogen and a double bond. Right? That alpha hydrogen, the hydrogen that is on the alpha carbon, is going to be somewhat acidic because it's sitting next to an electron withdrawing group. The carbonyl is an electron withdrawing group. There's a dipole, right? You have a partial positive charge on the carbon, and so the carbon that is directly adjacent to it, that hydrogen, is kind of acidic. It's got a partial positive charge. And so that's going to be the hydrogen that we use. For most ketones, the enol form is much less stable than the keto form. Phenol is different. Phenol is aromatic, and it's a little unusual in that its enol tautomer is more stable than the keto tautomer. But in general, the keto form is more stable. And the interconversion between the keto and the enol forms is called enolization. So sometimes we'll just use that word. So the interconversion between the keto and the enol forms, or in other words, the tautomers, is called enolization. Okay, so what's allowing this to happen? In basic solution, so we'll just do one example here. Under basic conditions, what happens? Well, in basic solution, a proton is going to be removed from the alpha carbon of the keto tautomer, and then you're going to form an anion, and it's going to have two resonance contributors. Here, let's draw one example here. So we've got our ketone here. I'm going to put in one of these hydrogens so that you can see what's going on. We've got a base, right? So we'll just draw a generic base. This is going to come in, and it's going to take this hydrogen away. And when it does, these electrons are going to come back and sit on that carbon. And what do you get? we get something called a carbanion. That carbon has got a negative charge. This is a carbanion. But you can imagine that now these electrons can delocalize up into the carbonyl. And we get our resonance, our other resonance form. This right here we call an enolate. Not quite an enol just yet, it's an enolate. We've got HB in solution, right? Because we use that to deprotonate our alpha carbon. And so we can protonate this, get our base back. And what do you have? We have an enol. So under basic conditions, that proton is going to be removed from the alpha carbon. The alpha carbon is right here. Let me put that in. So this is your alpha carbon, right? So the base deprotonates the alpha carbon. And you form a carbanion. Here's the deal though. The oxygen is better able to support that negative charge, and so that enolate is going to be more stable than the carbanion. So the enolate, in other words, is going to contribute more in the resonance hybrid, or it's going to contribute more to the resonance hybrid because the oxygen is better able to support the negative charge than the carbon. So you have a carbanion, it's in resonance with an enolate. The enolate is going to be the contributing resonance structure when you do chemistry with this. In acidic conditions, things are similar but just a little different. So we have acidic conditions. Where you're going to protonate the oxygen of the carbonyl in the ketotautomer. And then water is going to remove a proton from the alpha carbon, forming the enol. So this is going to be pretty similar. It's just instead of taking the hydrogen first under basic conditions, we're going to protonate the carbonyl, just like we're activating the carbonyl, right? So we take, say, use the hydronium ion as our acid. It makes it a little easier because we know what we're left with. So we're activating this carbonyl. And now along comes the conjugate base of that acid, which happens to be water, right? So water is going to deprotonate the alpha carbon. It's going to take a hydrogen away from the alpha carbon. And then what is going to happen? This is going to form a double bond and give electrons back to the oxygen to quench the positive charge. And you get your enol. Either way, you get your enol. So again, the acid, right, the hydronium ion, whatever, is going to protonate the oxygen of the carbonyl and of the ketotautomer, right? And then the water, or the conjugate base of that acid, whatever you got, is removing a proton from the alpha carbon to form the enol. How do these things actually react, though? So these enols, how do these enols and enolates react? That carbon-carbon bond, the double bond of an enol, suggests that it's a nucleophile. Remember alkenes? So we could use that as a nucleophile. But the enol is more electron rich than an alkene because the oxygen atom donates electrons by resonance. So in other words, an enol is going to be nucleophilic just like an alkene, but it's going to be more nucleophilic. It's going to be a better nucleophile than an alkene. So we can draw this out. So we'll just take our generic enol. How does it react? Well, what if we took these electrons and put them here? So again, the enol is going to contribute more, right, to the resonance hybrid because the oxygen is electron donating. So here's our carbanion. So we've got the enol form and a carbanion. If that's easier to see why this is nucleophilic, there you go. So carbonyl compounds that form enols are able to undergo substitution reactions at the alpha carbon. So at that alpha carbon, let me draw what I'm talking about. So if I have R, this right here is the alpha carbon. So that's where we can do our substitution reactions. And of course on the other side as well. So that R group on the other side, if that's a carbon, it's got some hydrogen on it, go to town. We're going to try to keep this as simple as possible. If you can imagine there is another alpha carbon on the other side, and there is because it's a ketone, then this can get pretty messy pretty fast, right? So under acidic conditions, let's talk just a little bit about that. So you're going to have water removing a proton from the alpha carbon of the protonated carbonyl compound, and then the nucleophilic enol is going to react with an electrophile. So under acidic conditions, we've got water removing, or some base. Let me put some base because that's not fair. The conjugate base, I should say. The conjugate base of the acid. It's sometimes water, so that's fair. Will deprotonate the alpha carbon. And then the nucleophilic enol, so then the resulting nucleophilic enol will react with an electrophile. And that will put a new group on the alpha carbon. What are you doing? You're going to be subbing or substituting an electrophile for a hydrogen. So this is otherwise known as alpha substitution. We can do this under basic conditions as well, right? We're going to deprotonate first with the base. So the base is going to deprotonate the alpha carbon. And then the nucleophilic enolate will react with the electrophile. Okay, so just so you guys know, enolates are better nucleophiles than enols. So let me just put that down there. So enolates are better nucleophiles than enols because they are negatively charged. So either way is fine. We usually do these reactions under basic conditions because enolates are better nucleophiles than enols. They have a negative charge. Let's talk about a very specific type of alpha substitution. This is called the aldol reaction. This is not named after somebody. This is named after what you get. So for example, we have talked already about aldehydes and ketones reacting as electrophiles, right? So that partially positive carbon on the carbonyl can be attacked by some nucleophile. We just talked about how an aldehyde and a ketone can be made into a nucleophile, right? We deprotonate the alpha carbon. You either make the enolate or you have the enol, right? And so the aldol reaction actually features these molecules behaving both as an electrophile and a nucleophile. So two equivalents of an aldehyde are going to get you, let's see, let me write this down. So we can have reaction of two aldehydes. One of them is going to be deprotonated, right? And it's going to be the nucleophile. I'm going to deprotonate and make the enolate. So that alpha carbon is going ahead and attack the carbonyl of the other aldehyde. So one of those aldehydes will be an electrophile. One of them is going to be turned into a nucleophile, and we're going to do chemistry with both of them. So this is going to produce what's called a beta hydroxy aldehyde. I can react two ketones and that's going to get us a beta hydroxy ketone. And here's one your book does not talk about. It gets a little messy. The stereochemistry can get pretty interesting. We can produce a pile of products pretty quickly, but you can react an aldehyde and a ketone. And so from that, you get, that's our mixed aldol, and we're going to end up, probably, we're not going to talk about that in Chem 42. You can save that for 142 and grad school if you like. You end up producing quite a few products. If you can imagine deprotonating the ketone, there's two alpha carbons there. So, you know, it's like you can just imagine the array of products that you can come up with. And I should say, your book doesn't talk about this, but if you're the person doing this chemistry, the aldol reaction with aldehydes is usually pretty messy. You end up with a bunch of byproducts. Aldehydes are really reactive, and we already talked about why. What does this look like, though, if I reacted two aldehydes? So let me just draw out what actually happens. So if you want to draw out the generic reaction, so for aldehydes, if I just put a 2 here, and I end up with, say, let's draw something pretty simple. What do you end up getting? So I'm going to deprotonate this. And I'm going to get there is the beta carbon. So alpha is next to the carbonyl, that's the beta. So that is a beta hydroxy aldehyde. How Did this just happen? Okay, so let's just do this out and see what's going on. So I'm going to take my aldehyde. I'm going to draw this just a little bit more suggestively, because I'm going to use one of those, right? One of those hydrogens. I'm going to take my hydroxide. That's going to be my base. And I'm going to deprotonate this thing. And what do I get? I'm just going straight for the enolate. Now what? Along comes our electrophile. Now we have our nucleophile here, right? We have our enolate. Let me write that out. This is our enolate. What ends up happening is these are going to come down, and we're going to end up attacking. Let me draw out the other aldehyde here and get it ready to be attacked. So I've got there you go. So those electrons come down, and we're going to attack right there. So what do you get? You end up with so there was the aldehyde that got attacked. And where did it get attacked? Right here. What did it get attacked by? This other carbon. Right? It's this thing right here. So we're going to form a bond between this carbon and this carbon. So there's one of them. There's the other one. What else is on that carbon? CH3. What else is attached to that carbon? And if I have in solution conjugate acid, because we've used the hydroxide ion, right, to deprotonate the alpha carbon, so I have some water floating around, I can protonate that, and I get, let me draw this a little clearer. So here is the beta carbon. We have our beta hydroxyaldehyde. All I did was just extend that chain, right? Make it just a little easier to see. I can do the same thing with a ketone. Let's draw a ketone. So we've got two ketones. So for ketones, I can have, let's see, just keep it easy and use acetone. We'll have two of these. Hit this with a base and deprotonate the alpha carbon. What do I end up getting? I end up getting beta hydroxy ketone. So there's your beta carbon there. This is your beta carbon. Beta hydroxy ketone. When you are being asked to identify, hey, is this an aldol? How do you see what happened here? If you see a beta hydroxy aldehyde of beta hydroxyketone, chances are this thing happened by an aldol reaction, or it could have happened by an aldol reaction. And the same mechanism happens, right? So if you want to draw this out, we can. We can have CH2. Actually, let me expand this. Let me just start over here. We got, because we have so few carbons, I'm just going to expand this out. So my hydroxyl group is going to come in, and I'm going to snag that hydrogen, make the enolate. You can go through the carbanion and do the resonance, it's fine. I'm going straight for the enolate because it's going to be our more contributing resonance form. So there's your enolate. And that is ready to attack. And it's going to attack another ketone, so another acetone. So CH3. So these are going to come down. And now that thing is one heck of a nucleophile. We'll attack that. And what we get is what? So we can draw this out like this was the thing that was just attacked. CH3. What did we do? We attacked with this carbon. We attacked that carbon. So that was the carbonyl, right? And this carbon right here came from the enolate. So what was on that enolate? CH2. And then what else? That other carbon, right? So what's on the other side over here? And then we have some water in solution because that's our conjugate acid. What you get, and I'm going to draw this out just a little bit easier to see here. I'm going to flip everything around and just draw it in a straight line. So I've got so this right here is your beta hydroxyketone. Here's your beta carbon right there. So this is a beta. Right? So we've got what? You want to highlight this? So we've got our two carbons right there. So this is our aldol reaction. You can imagine if I were to deprotonate a ketone and react it with an aldehyde, and you were considering stereochemistry, depending on what molecules you had, this could produce a lot of compounds pretty quickly. The important thing to notice is that beta hydroxy group and the fact that you have your carbonyl back again, right? So you get beta hydroxy aldehyde, beta hydroxy ketone. Chances are it was formed by an aldol reaction. So this is going to cap off chapter 9. We're going to start chapter 10 on Wednesday, carboxylic acids and their derivatives. It's going to be easygoing for us, and especially in terms of nomenclature, because we've already talked about the nomenclature of carboxylic acids a bunch of times. The chemistry of its derivatives, though, will be interesting for us and a little bit new. We'll be making esters. We'll be using acid chlorides and reactions. I'll introduce anhydrides, probably amides. And so we'll start all of that on Wednesday.